Physics Notes, Unit 17. We'll do a little review on waves, and then we'll apply that specifically to sound waves and hearing and these incredible sensors that we have on both sides of our head. Incredibly designed and engineered, and it's a miracle that they work. We'll talk about that as we go along here. But a quick review. A wave in general is a disturbance, a wiggle, a jiggle that transmits energy without transmitting a physical medium or material. The waves travel through a medium, and we went over the different types of waves in Unit 16. You can categorize them by transverse, where the vibrations of the material are perpendicular to the way the energy transfers, or longitudinal, of which sound is one of the best examples, pretty much the only example, other than a slinky, which we won't really talk about a whole lot. I'll show you a slinky here in a few minutes, but sound is the best example. If I ask for an example of longitudinal waves, sound, where the vibrations of the air particles are forward and backwards. I'll show you a video in a second, in the same way that the energy is propagating or traveling through the air from point A to point B. The other way to categorize waves was by mechanical and electromagnetic. Sound is definitely a mechanical wave. It requires a medium, air particles or even liquids or solids, like we talked about in Unit 16. The only thing that are electromagnetic waves are like light, X-rays, radio waves, and more on that to come. But we're going to be focusing on sound here. A lot of really cool stuff here. I mean, it relates to music, a lot of practical applications here. I'll save the math part for the end. It can get very, very mathematical. We won't do a lot of the math here. We'll do some of it, but we'll stick mostly with the concepts in this chapter, and I'll finish up with the math. All right, so sound. It's a longitudinal wave of alternating high-pressure compressions and low-pressure rarefactions. Sound can travel through liquids, solids, and gases. I'm going to show you a video here in a second, but when it's nice sound, when it's a very nice repeating pattern, and we can't see sound, I'm going to have some videos here that illustrate what sound is in these pictures at the bottom. All these dots represent air particles, which we can't see, but we have these incredible detectors, like I said, these incredible detectors that are miraculous, that can detect minute little vibrations of very small air particles. It's incredible how sensitive and how well our ears work, and we take them for granted. But when the pattern is nice and very repeating, it sounds good, it's music. When it's sort of a random pattern, then it's noise. And if there's no vibrations, it's just no noise at all, then it's obviously quiet. Also, like, it kind of answers that question, the age-old question, like if a tree falls in a forest and if no one is there to hear it, does it actually make sound? And from a physics standpoint, yes, it makes sound. It makes the air vibrate. It's a noise kind of sound, but if somebody were there, they could pick it up, or any kind of instrument was there, they could pick it up. It does vibrate the air, just that nobody measured it or detected it. As we also learned in the last unit, sound travels at 343 meters per second in room temperature air. That's about 770 miles per hour. Room temperature is basically 20 degrees Celsius, which is roughly 70 degrees Fahrenheit. There's a table in your book, table 17.4, which tells you the different speeds in different materials. It's faster in water because the particles are closer together, essentially, so the transmission of the signal can go faster. And once again, when sound travels underwater, it's not the water that's traveling, it's a vibration that's traveling. Energy is traveling, not the water itself. The water particles just vibrate. And then, in solids like steel, it travels even faster because the particles are even closer together. So if I reference other materials, I'll have a table there where you can look it up. But basically all the problems we'll be dealing with are going to be sound and air, which is obviously the most typical. So let me show you, let me just talk about this picture down here. All right, tuning, this one here, this is a tuning fork. If you've never had the opportunity to play with a tuning fork, they're kind of fun in the olden days, and still maybe today, you use a tuning fork to tune instruments. Nowadays they have electronic tuners, but they're kind of fun because you can put them by their ear and they just sound nice. They're like, one of the typical tuning forks is a middle C, 256 hertz. That is what all middle C's are in all instruments. They happen, like if you play a middle C on a piano, middle C on a tuning fork, middle C on a oboe, middle C on a flute, it's all by the physics standpoint the same note. It's defined to be 256 hertz, vibrations per second of the air particles. They will all sound a little bit different on those different instruments because there's other frequencies mixed in with that bass frequency. But a tuning fork is one of the most pure kind of notes that you will have with a few other what we call overtones mixed in. We'll talk about that, harmonics. But this demonstration right here, a speaker, basically all a speaker is in a whatever it is, your phone, your radio, all it does is really it's just a piece of paper. And there's like a magnet and a coil of wires, which we'll talk about in a couple of units. But it makes the paper vibrate, and the paper vibrates. It pushes on air particles, pushes out and in and out and in. That's what causes these compressions. So we have 1, 2, 3, 4, 5, 6 compressions here, and then the rarefactions between them, and they bounce against your ears. Those air particles. It's the same air particles hitting your ear, in and out, in and out. So it's not the air particles once again traveling from the speaker to your ear, but that signal transfers, and you detect that, and you've learned how to decipher the special vibrations and an incredible transformation of energies and signals to your brain through electrical connections from your cochlea to your brain and so forth. You guys probably know more about that than I do. We'll talk a little bit about the ear here in a minute. But this, once again, this depiction with this green wave is showing you how you can match up a transverse wave with a longitudinal wave, because sound is a longitudinal wave here. But the compression would be like a crest, and then the rarefaction like a trough. Let me show you a tuning fork. I might have shown you this in Unit 16, but I want to show you this again just to review it. So we have your tuning fork here. I'm going to turn this on in a second. Well, let's see what happens here. So all these dots are air particles, and we have our compression. Like I think I showed you this in Unit 16. If I start this up, the tuning fork tines go back and forth, and as they go out, they make a compression. And the video here is a little bit jerky, but the compressions are going outward. All the white dots are just vibrating back and forth, parallel to the way the sound wave travels. And they're spheres in real life. So that's a quick review of sound waves. But anything that produces sound, even my voice or a musical instrument, makes this same type of regular pattern going out from that particular source. And that is a sound wave. And if it's music or a nice note, and it sounds good to our ears. All right, so now some terms that are specific to sound waves. Pitch is the frequency of a sound wave. So frequency is a general term for how many cycles per second. But pitch is the frequency of a sound wave. The average human can hear from 20 hertz to about 20,000 hertz, at least when you're young. I've lost a lot of the high frequency range. Old people like me, maybe can get up to 12 or 13,000 hertz. So that's when there's those high frequency mosquito ringtones that they used to use. The old people like myself can't hear those. Anything above 20,000 hertz is ultrasonic. There are some animals that can hear above 20,000 hertz, like dogs and bats and I guess a few others. Infrasonic is sound frequencies, pitches below 20 hertz. Loudness, the intensity, which we defined last unit, which is power over area, is measured in decibels here. And it's a weird unit because it's D, capital B. It's also logarithmic, which I will show you in a chart here in a few minutes. Basically, it goes up by multiples of 10. For example, 60 decibels is 10 decibels louder, but it's 10 times louder. All right, so it doesn't look like much there. But when you look at like say 50 versus 20, well, the number 50 is just over twice as big as 20. But what you don't look at it that way for these logarithmic scales. You just count by tens in a sense, like from 20 to 30 to 40 to 50. That's 30 decibels. What's important there is the 3. 30, but the 3, that's a 10 to the third power. So 50 decibels is 1,000 times more intense than 20 decibels. It's logarithmic. You'll see this in a chart in a few minutes here. And there's a chart over here that shows you the loudness of different sounds, the intensity of different sounds. It's kind of interesting. And a lot of these depend on how far away you are. They don't all tell you how far away you are, but like for an average whisper 4 feet away, 20 decibels. If you're in a standard restaurant, once again, it depends on the restaurant. 50 decibels, busy street. automobile horn from 23 feet. It depends on the automobile horn, but the average automobile horn, 100 decibels. All right, timbre, T-I-M-B-R-E. It's the tone of a sound. It explains why, like for example, the middle C from a physics standpoint, even from a music theory standpoint, is 256 hertz by definition. On a piano, if you hit the middle C, it's 256 hertz. If you play that on an oboe or a saxophone, it's 256 hertz. If you sing that note, it's 256 hertz. So why do all those instruments have a slightly different sound to that note? Well, because they have different other notes mixed in, what are called overtones and harmonics. That's the timbre. So that's what gives things a different sound, even for the same note, because the same bass note, the fundamental note, is still 256, but there's other things mixed in with that. A fan is a perceived loudness. So it kind of connects with loudness up here. This loudness up here is as measured on a machine that measures decibels. It's very objective, quantifiable in numbers. A fan is more a perception. There's a chart in the book 1738. Here's the chart, okay? And what it does, it shows you the connection between fans and decibels. Now on the side scales, these are linear, like a normal scale, like 20, 40, 60, 80. On the right-hand side are the fans, all right? Each line, okay, is a line for it that's on here is a line of equal fans. So everything on that line is 0 fans. One thing that implies here in this diagram is that you can't hear anything below, anything below that, that's your threshold of hearing. So for example, if there's a sound of, let's say, 40 decibels, a 40 hertz, this bottom scale is frequency. So if you have 40 hertz sound, okay, you can't hear that at 10, 20, 30, 40, 50 decibels. It's got to be at least like almost 60 decibels before you can hear that, the typical human, all right? But middle range frequencies you can hear with lower sound levels. In fact, some of these are are basically in a negative territory. So, for example, 200 hertz sounds, you can at 200 hertz, at 200 decibels, you can start hearing those. Anything below that, you still can't hear it. 1,000 hertz, okay, you can hear that at 0 decibel levels. So anything below that bottom curve, you can't hear. It's your threshold of hearing. But let me talk more about this logarithmic scale here in the bottom. For example, if I go from 0 right here on the left to 100, there's a distance there. It's like 3 centimeters. Okay, but if I measure that same distance again from here, I should get to 200. So if I go over here, this should be 200 right here. And then over here, this should be 300. But they're not going up linearly. It's going up logarithmically. In other words, if I take this distance, then I take that same distance again, even though it should be 200, it's times 10, it's 1,000. Then I take that same distance and go that same distance again to the right. From 1,000, it should go to 2,000, but it doesn't. It goes to 10,000. You keep multiplying by 10 every time you go along that same distance. That's what makes it logarithmic. We're not going to do the math on that, but I may have you read this scale. Now, what I did say, I sort of skipped it. You can go back up. Well, I can go back up here. At 1,000 hertz, by definition, the level of fans equals a decibels. That's your perceived loudness, what you feel how loud it is. Okay. So, for example, I could ask you, like, say at 4,000 hertz right here. And once again, all these dip down. What that means here, all these downward dips, means that those sounds are easier for you to hear on the average because they don't need to be as loud. Okay, the higher these lines are, the louder that sound needs to be for you to hear it. All right? So, or the louder, the louder it's perceived, the higher these are. So, for example, up here at 1,000 decibels, which is really loud. I think, some things are not 1,000, 100. Automobile horn from 23 feet, 100 decibels. Okay, 100 decibels for you, okay, or the average human, if you follow that line over, that's, okay, that's your, what line is that? That's your 100 fan line as well. All right. Now, always they're equal to each other at 1,000, but let me give you another example. Let's take the 30 fan line, which is the 4th line from the top. Okay, the 30 fan line. All right, so at the 30 fan line, it's your perceived, how loud you feel it is. Okay, how loud it feels to your ears. So if you take 10,000 hertz, follow that up to 30 fans, okay, everything on that line sounds as loud to you. Okay, so at 10,000 hertz sound will sound as loud to you if it's played at a particular. If it's played at, it's actually being played at. It's being played at 40 decibels. It's actually 40 decibels. It's measured on a machine. So if you have a 10,000 hertz sound played at 40 decibels, it doesn't sound like 40 decibels to you. It sounds like 35. It's not going to sound as loud as a 40 decibel sound. Okay, it's going to sound a little bit not as loud. But a 4,000 hertz sound, all right, played a 4,000 hertz sound played at about, if you go over here, about just above, it's about 12 decibels. It's going to sound the same loudness. We're supposed to be on what, the 30 fine line? Okay, it's 30 fine line. 30 fine line, I think is what I said. 30 fine line at 4,000 hertz. Okay, that's being played at like just under 30 decibels. So at 30 decibels, if you play a 4,000 hertz sound at 30 decibels, actual measurable level, it's going to sound as loud to you as a 10,000 hertz sound played at 40 decibels, because all on that 30 fine line, anything on that 30 fine line sounds the same loudness to you, even though they're not the same loudness, as measured on a machine that gives you actual readings of actually how loud it is. That's your perceived loudness. These lines represent how everything on that line represents something that sounds the same loudness to you. So basically at lower frequencies, okay, those sounds, okay, have to be played really loud for you to hear them. Otherwise you don't hear them, number one. And number two, you will hear them like 80 decibels. Let's go to the second line, the 10 fine line. The 10 fine line. At 10,000 hertz right here where I'm at right now, that is 20 decibels. So at 20 decibels, that's going to have a perceived loudness of 10 fines. All right? But for you to hear it at 10 fines, at a lower frequency, if I follow it all the way along to say like 40 hertz, I need to have it played at 60 decibels. At 60 decibels, it will sound the same loudness. At 40 hertz, if I play a 40 hertz sound at 60 decibels, it will sound just as loud as a 10,000 hertz sound played at 20 decibels. So you have to look at that for a while. There's a lot going on there. That's fine. It's perceived loudness. Then you have the incredible ear, and all the careers involved with ears. Well, it was more than that, but your ears and your eyes and your systems in your body. But you guys, a lot of you guys are pre-med and biology majors, and you might be audiologists someday, or acoustical engineers, which are basically more on the physics side of things. But it's incredible what's in your ear. And this is a simplified picture. You have your outer ear, your middle ear, your inner ear, the auditory nerve, the auditory canal, the cochlea. There's a fluid in there. Your ear is also responsible for like keeping your balance because of these semicircular canals. It's got the three smallest bones in the body. The malleus, the incus, and stapes. When I was a kid, we used to call those the hammer, the anvil, and the stirrup. The hammer, the anvil, and the stirrup. But the official names are malleus, incus, and stapes. I'm not sure I'm saying that right. But it's incredible that this structure works. And then it keeps your balance, and it's an incredibly well-engineered design. It's a miracle that it basically works. There is, so I almost get goosebumps when I think about how these things work and how they can perceive just little bitty air particles bouncing against this eardrum, which is really tiny. There's very little movement in that, connected to these really tiny bones that move and then send some fluid vibrations through some fluids that have little hairs, little cilia hairs in this spiral cochlea. So I'm glad that you guys are going to be working this out someday so you can help keep us all with good hearing as we get older. So other careers: acoustical engineering, audiologist, otolaryngologist, can't even say it right, ear, nose, and throat doctor. Musicians deal with sound and hearing. Interpreters, sign language is also an important job. So a lot of things involved with sound and hearing. All right, going back to something that is for all waves. But we'll apply this mostly to sound waves here in this chapter. But you have two very important ideas here: constructive and destructive interference. And constructive interference is illustrated with diagram A. If you have two waves, okay, if you superimpose them and put them together, you get a larger wave. That's constructive. They add together and give you a wave that's twice as large if they're, what they say, in phase, matched up. All right. If it's sound, it's going to be two sounds put together give you a really loud sound. If it's light, two light waves put together give you really, really bright light. If it's water waves, they give you really, really tall waves that you like to surf on and things like that. But you have the opposite idea. You have, this is totally destructive. And then there's all the variations in between. You can have somewhat constructive, and it's a little bit messier. We're only going to deal with the perfectly constructive in A or the perfectly destructive in B. We're not going to, well, C we'll talk about a little bit of both, but we're going to focus on A and B here. So like when one wave is going up and down, the other one's going down and up, you put those together, it cancels out. That's like noise canceling headphones. It can cancel out a sound. It only works well if you have a nice repetitive sound like background hiss, like in an airplane or a musical note. You can get rid of that if you have some noise canceling headphones that create the opposite sound that you're trying to cancel. And once again, if it's sound waves, you put that together, you get quietness. If it's light waves, you get dim light or darkness. And if you have water waves, you get low waves or just flat water. This gives you more of a kind of a two waves that aren't the same frequency, and you put them together. The superposition, they call this the superposition, the composition of the two waves together gives you a repeating pattern that has constructive and destructive. This one here, which I'll talk about later on, which is illustrative of beats, where this bottom pattern is the two put together, where it gets when it's fat, it's loud. It goes loud, soft, loud, soft. These are sound waves. This only happens when you have two waves that are very, very similar in frequency. In C, they're quite different in frequency. This would be more of the example of like the timbre example I was using before. Like the top wave is like the fundamental wave, like the middle C on a piano, or you're singing a middle C. This other note might be mixed in. It's similar to, it's like maybe like twice the frequency of the 256, but it gives you another pattern that sounds like a nice musical note, but it has some characteristics of both those waves. So it's not completely random in noise, and it might sound good. This typically doesn't sound good. I'll give you some examples in a few minutes here, but this is beats, and when you have musical instruments that have beats, basically it means they're out of tune, and it doesn't really make this sound good. This one over here on the left might sound good. The one on the right here for beats, which I'll come back to, doesn't. All right. Standing waves. Standing waves are a fixed pattern of nodes and antinodes, which I will show you a picture of here in a minute. I'll give you a definition. So a fixed pattern of nodes and antinodes when a wave is reflected back on itself. A node is a location of no displacement or very little or no vibration. Antinode is wild vibration of the particles in your wave. Basically, musical instruments of all kinds. Generate standing waves. This is the basic principle of musical instruments. They generate standing waves of a sound, nodes and antinodes. So I'm going to try to show you a little video here and then talk about standing waves so you can see the visual. Let me see if I can do that. So here's an example of standing waves. This is a long spring that he's going to shake and make waves, different wave patterns. And basically a standing wave is a pattern that looks like it repeats itself. All right, that's a wave pulse. That's what we call a pulse. It goes down and reflects off the end. All right, it's interesting also, it flips sides. It flips sides when it goes down. Comes back. You could measure the speed of that just using a distance time. You could figure out how far that is and time it. We're not going to do that. You might do it in the lab. Now he's going to shake it. This is what they call the first harmonic. I'm going to freeze it here for a second. I'm going to stop it. Okay, so I stopped it. So bottom line is this end down here at the very end is a fixed end. It's called a node. That's not moving at all. The middle part of this, it's kind of like a jump rope right now. He's actually not twirling it around and around like a jump rope. He's just going back and forth at a low frequency, just keeping up that pattern. But he has to keep that rhythm. If he doesn't use that rhythm, he doesn't get that pattern. Okay, that's called it's called a standing wave. All right, so you have that antinode, that big motion in the middle. Technically, if he stopped moving his hand right here, he needs to use his hand to keep it going because there's friction. But if he stopped his hand at this end, it's called a node, it would just keep going back and forth, back and forth, back and forth as a fixed pattern. It's called the first harmonic, or it's called the fundamental. I'll come back to that in the notes. Now he's going to double his frequency, or her frequency. Let's see if they do that. So there's the fundamental. So here we go. They're going to double the frequency now, and you'll see, there we go, twice the frequency. It's called the second harmonic. I'm going to freeze it here once they put the letters on there. There's two bumps. Those are two antinodes. All right, so I'm going to stop it. So you have, that node is down here at the end. There's a node in the middle now, and there's two bumps. Those are called antinodes, where there's a lot of movement. Like if you, once again, were the a particle in a spring, okay, that's the medium right now. You're just vibrating back and forth. The wave energy is going down and back. But actually, in this case, unlike at the very beginning of this video, you saw the wave go down and come back and go down and come back. Okay, you could see the wave traveling and carrying energy from point A to point B. Now you don't really see like the wave going down and back, down and back. You just kind of see these bumps going back and forth. That's why it's called a standing wave, like it's not going anywhere. Even though there still is energy being transferred, it doesn't look like it. So it's a standing wave. And this is what happens with musical instruments, with stringed instruments for sure. So any kind of stringed instruments, this happens on a smaller scale. The string vibrates according to that fundamental you just saw, and it has these harmonics or overtones mixed in with the fundamental. The fundamental is just that one big antinode in the middle. But it also happens with air columns and pipes. It's a little bit more complicated with wind instruments, but string instruments for sure. This is, if you could actually take a picture of the string, it vibrates back and forth. If you strum a guitar string at 250, or so it plays the 256 middle C, it's going to vibrate back and forth at 256 times. It looks like a blur, but it's going to have some of this mixed in with the fundamental that was the first one. All of that together will make it look kind of random, but it's not random. It's a standing wave of nodes and antinodes. Let's go to the third harmonic. All right, let's see. And he keeps going to the fourth. So now they're going to try to, he's got to go 3 times the frequency though. So if the first frequency was 10 hertz, then it was 20 hertz. Now it's 30 hertz. I'm going to try to freeze it once they put the letters on here. So swinging back and forth. There we go. I'm going to stop it. Whoops. All right. So you got 3 bumps now. That's spelled out with the letter A here. This is an antinode. If you were on that spring, as a piece of that spring, you'd be going crazy right now, back and forth, back and forth. But if you were right here by this N, you're barely going anywhere. It's hardly going up and down at all. So you have nodes and antinodes. Nodes are no displacement. Antinodes are the big bumps. All right, so we're going to come back to that, but that's an example of a standing wave. It's a good way to do that, to illustrate that with slinkies and springs. It works even better on the floor, but they don't have a picture of the floor here because then everything looks the same size. It's a little it's distorted from the end view here, but it gives you a good example of a standing wave.